Every process has a voice. Machines, materials, and methods all vary, and if you listen to that variation the right way, the process will tell you when something has genuinely changed, and when it hasn't. This is Control Charts in Manufacturing, a plain English introduction to statistical process control. Over the next quarter of an hour, we'll cover how to see the voice of the process, detect real problems, and prove your process is capable. Let's begin. Here's the plan. By the end, you'll be able to do 6 things. Explain variation and why the difference between two kinds of it drives every decision. Select the right chart for any type of data. Build a chart and calculate its limits. Read the signals a chart gives you. Prove capability with the indices your customers ask for. And put it to work on the shop floor in a way that sticks. 6 steps, from theory to the factory floor. First, why bother at all? Traditional inspection finds defects after they're made. You pay to produce scrap, then pay again to find it, and the damage is already done. Statistical process control flips that around. It monitors the process in real time, so you can act on a trend before parts ever go out of tolerance. That shift, from detection to prevention, is the whole point. It's 5 to 8 times cheaper to prevent a defect than to detect and rework it. A stable, charted process is also a predictable one. You can quote your capability, reduce sorting, and cut the cost of poor quality. Walter Shewhart invented the control chart at Bell Labs back in 1924, and the balance he chose, 3 sigma, still runs the factory floor today. Everything starts with variation, so let's be precise about what it is. There are 2 kinds of variation, and telling them apart is the entire job. Common cause variation is the natural, ever-present noise of a stable process, many small sources adding up, predictable within limits. It's the process simply being itself. Special cause variation is different. It's an assignable event. A tool breaks, a new batch arrives, someone changes a setting. That's a signal. Something specific has happened, and it's worth investigating. A control chart exists to separate the signal from the noise. Get that wrong in either direction and it costs you. React to common cause as if it were special, and you over-adjust and tamper. Ignore a special cause as if it were noise, and you miss a real problem. The control limits draw the line between the two. That first mistake, tampering, deserves a warning of its own. Deming's famous funnel experiment showed that if you adjust a stable process toward target after every single reading, you don't reduce variation. You actually increase it. Leave a stable process alone. It helps to remember there are 3 states a process can be in. In control and capable. Stable and meeting spec, the goal. Just monitor it. In control but not capable. Stable, but its spread is too wide. You have to improve the system itself. And out of control. Unpredictable. Remove the special causes first, because until you do, capability is meaningless. So what does a control chart actually look like? 3 things. A center line, the average of whatever statistic you're plotting. Control limits above and below it, set at 3 standard deviations of that statistic. That's the voice of the process. And 3 zones on each side of the center line, each 1 standard deviation wide, which the pattern rules use. The simplest signal of all is a single point falling outside the control limits. That's the first rule, and often the only one you need. Now the single most important idea in this whole subject, and the one most often confused, control limits are not specification limits. Control limits are the voice of the process. They're calculated from your process data. They tell you what the process actually does, and they only move when the process itself changes. Specification limits are the voice of the customer. They come from the drawing or the requirement. They tell you what the process should do, and they apply to individual parts. Never plot specification limits on a control chart. Comparing the two is a separate and valuable exercise. It's called process capability, but it only means anything once the process is in control. Before you plot anything, you have to collect the data the right way. This is called rational subgrouping, and it's where many charts quietly go wrong. The principle: form your subgroups so that the variation within a subgroup is only common cause noise, and any special causes show up as differences between subgroups. In practice, that means sampling consecutive parts from one stream over a short interval. The within subgroup range is what sets your limits, so it must capture only natural noise. A few rules of thumb. Subgroup size is usually 4 or 5 for variables charts. Collect at least 20 to 25 subgroups to establish reliable limits. Sample often enough to catch shifts, and keep it to one machine, one cavity, one stream per chart. With the data collected properly, let's build some charts. The choice starts with one question. What kind of data do you have? Variables data is measured on a continuous scale: length, weight, temperature, diameter. Attributes data is counted, pass or fail, or a number of defects. For variables data, the chart depends on your subgroup size. One reading at a time uses an individuals and moving range chart, or IMR. 2 to 9 uses the X-bar and R chart. 10 or more uses X-bar and S. For attributes, it depends on what you're counting. Defectives, whole failed items, use a P chart when the sample size varies and an NP chart when it's constant. Defects, individual flaws, use a C chart for a constant unit and a U chart for a varying one. Variables charts always come as a pair. One chart for the average, which is the location, and one for the spread, which is the variation. And here's a rule that trips people up. Always read the spread chart first. If the spread is unstable, the limits on the averages chart simply aren't valid. To calculate the limits, you use a small set of standard constants, A2, D3, D4 for the range chart, and so on. Those constants bake the 3 sigma maths and a bias correction into a single lookup factor, so you don't have to derive anything. You just read the factor for your subgroup size and multiply. Let's build the workhorse, the X-bar and R chart, in 6 steps. 1. Collect 20 to 25 subgroups of 4 or 5 consecutive parts. 2. For each subgroup, compute the mean and the range, where range is simply the largest value minus the smallest. 3. Find the center lines, the average of the means and the average of the ranges. 4. Calculate the range chart limits using the D constants and check the range chart is in control first. 5. Only if the range chart is stable, calculate the average chart limits using the grand average plus and minus A2 times the average range. 6. Plot everything, apply the rules, remove any special causes, and recalculate. Spread first, then location, always. Let's put numbers on it. We're charting a shaft diameter, subgroups of 5. The grand average comes out at 25.000 millimeters, and the average range at 0.0395. For a subgroup of 5, the constants are A2 0.577, D4 2.114, D3 0. The range chart upper limit is D4 times the average range, about 0.084, with a lower limit of 0, and the range chart is in control. Good. Now the average chart. Upper and lower limits are 25 plus or minus 0.577 times the average range, so about 25.023, and 24.978. And look at subgroup 16. Its average is 25.040, above the upper limit. That's a special cause. Investigate it, exclude it, and recalculate the limits. 2 more variables charts round out the set. The X-bar and S chart is used when your subgroups are 10 or more. It replaces the range with the subgroup standard deviation, which is a more efficient measure of spread once samples get large. And the IMR, or individuals and moving range chart, is for when you only get one reading at a time, slow, expensive, or batch processes where a single measurement per period is natural. Instead of a range within a subgroup, it uses the moving range, the absolute difference between one reading and the next. The maths differs slightly, but the logic is identical. Spread chart first, then the individuals chart. Now the attributes family, for counted data. The key distinction is defective versus defect. A defective is a whole item that fails. It follows the binomial pattern, and one item is either good or bad. A defect is a single nonconformity, and one item can carry several, that follows the Poisson pattern. From there it's about sample size. For defectives, a P chart for fraction defective when the sample size varies, an NP chart for number defective when it's constant. For defects, a C chart when the unit of inspection is constant, and a U chart for defects per unit when it varies. 4 charts, 2 simple questions. A quick attributes example: 25 samples, 200 units each. Total defectives across all of them, 298. So the average fraction defective is 298 divided by 5,000. That's 0.060, or 6%. The standard deviation of that proportion works out to about 0.0168. The upper control limit is 6% plus 3 of those, about 11%. The lower limit is just under 1%. Then sample 18 comes in at 13%, above the upper limit. Special cause. Investigate. You can build a chart now. The next skill is reading what it's telling you. The most important signal is the simplest. 1 point beyond a 3 sigma control limit. In a stable process, there's only about a 0.27% chance of that happening by pure luck. So when you see it, treat it as real. It catches large, sudden shifts. And as the statistician Donald Wheeler noted, in most applications, that one rule alone is enough. Why 3 sigma? It's a trade-off. Set the limits too tight and you get false alarms. You chase noise and start tampering. Set them too wide and real shifts slip through unnoticed. Schuhart's 3 sigma is the economic compromise. Roughly 1 false alarm in every 370 in-control points. Extra rules can raise your sensitivity to small shifts, but they also raise the false alarm rate, so add them deliberately, not by default. Those extra rules are the Western Electric and Nelson rules. 8 tests in total, read against the zones. The original 4 came from the Western Electric Handbook in 1956. Nelson added 4 more in 1984 to even out the detection probability. What they buy you is sensitivity to small, sustained changes that a single out-of-limit point would miss. A slow drift, a run of points on one side of the center line, a repeating pattern. Trend and shift rules catch the quiet problems. Use them when small shifts matter enough to justify the extra false alarms. Reading the zones is straightforward. Zone C is within 1 sigma of the center line. Zone B between 1 and 2. Zone A between 2 and 3. In a stable process, about 68% of points fall in C, 27% in B, and 4% in A. When the actual mix departs from that, the pattern rules trigger. But a signal is only useful if it leads to action, and that's what an out-of-control action plan, or OCAP, is for. 5 steps. Stop and contain. Quarantine product back to the last good check. Investigate. Find the assignable cause. Correct. Remove it and verify the fix. Document. Record the cause and the action on the chart. And recalculate. Exclude the special cause points and update your limits if the process genuinely changed. A signal must always trigger a defined, documented response. Once your process is stable, you can finally answer the question the customer really cares about. Is it capable? Capability compares the voice of the process, its spread, with the voice of the customer, the specification. And it's only valid when the process is in statistical control. Keep that in your back pocket. Cp is potential capability, the tolerance width divided by 6 sigma. It tells you whether the spread could fit inside the tolerance, but it ignores where the process is centered. Cpk fixes that. It measures from the process mean to each spec limit and takes the worst of the two, so it penalizes a process for being off-center. The common bar is a Cpk of at least 1.33. For safety-critical characteristics, at least 1.67. PP and PPK use the same formulas, but with the overall, long-term standard deviation instead of the within subgroup spread. They describe performance across the whole run, drift and all. Back to our shaft. We estimate the process sigma from the average range as about 0.017 millimeters. The spec is 25 plus or minus 0.10, so a lower limit of 24.90 and an upper of 25.10. Cp is the tolerance of 0.20 divided by 6 sigma, about 1.96. Working out each side gives a Cpk of about 1.93. That's comfortably above 1.33, so the process is highly capable, and because Cp and Cpk are close, it's well centered. At roughly a 6 sigma level, you'd expect only a few parts per million defective, as long as it stays in control. A word of caution on those defect rates. They assume a centered, normally distributed, in-control process. Off-center or non-normal data will deviate, so always confirm normality before you trust a parts per million figure. And while we're on cautions, here are the classic mistakes to avoid. Don't put spec limits on the chart. Don't tamper, react only to signals. Don't calculate capability on an unstable process. It's meaningless. Don't mix streams within a subgroup. Don't trust limits built from fewer than 20 subgroups. Don't read the average chart before the range chart. Don't recalculate your limits so often that you chase them and hide real shifts. And don't assume normality blindly. So how do you make this stick on the floor? 5 stages. Prepare. Pick a critical characteristic and confirm your measurement system with a gauge study. Baseline. Collect your 20 to 25 subgroups, set trial limits, and bring the process into control. Deploy. Put the charts at the point of use, train the operators, and agree the reaction plan. Capability. Once it's stable, calculate Cp and Cpk and compare to the requirement. Sustain. Audit that the charts are actually used and recalculate only on real change. Remember the 6 takeaways. Variation has 2 types. Leave common cause alone. Investigate special cause. Match the chart to the data. Control limits are not specs. Read spread before location. React with an action plan. And capability needs control first. Aim for a CPK of 1.33 or better. Thanks for watching. If you'd like the workbook that does all of this maths for you, the SPC Control Chart Toolkit and the free CPK calculator are linked below, and you can read the full written guide on the QLaws Insights blog.